Good morning, everyone. And yeah, let's get back where we left off last time. So remember, we were talking about the notion of homomorphic encryption earlier in the um, encryption schemes or type of encryption schemes we looked at. Homomorphism was typically a problem, right? Like when we want to achieve CCA security, homomorphism is not just an issue, it makes it impossible to achieve CCA security because particularly homomorphism means malleability, the ability to take a ciphertext and change it into a related ciphertext. When we just talk about malleability, this modification might be, in some sense, untargeted, or yeah, there might not be the relation between the input ciphertext and the output ciphertext might not be sort of a functionality that we're looking for, but it's still good enough to sort of circumvent this restriction that a decryption oracle in the CCA experiment gives us, right? As long as we know sort of what the relation between these, or some aspect of what the relation between these ciphertexts is, it's okay. But in homomorphic encryption, we want the ability to precisely manipulate the message that's encrypted in a ciphertext, right? And the most basic, or one of the most basic types of homomorphism is additive homomorphism, something that El-Gamal gives us. So in El-Gamal encryption, let's see, where did I write this? Yeah, we can, depending on how we encode the message, we can achieve a simple additive homomorphism, which is already good enough for some applications, right? Like the example I gave here was something like basic elections, where we just want to do a homomorphic tally of encrypted votes. Okay, but we're gonna look at homomorphic encryption with a little bit more, with somewhat more power than just additive homomorphism. And the general notion of homomorphic encryption, which we introduce here, allows us to, well, just specifies some class of functions, right? This is sort of the parameter that specifies homomorphic encryption scheme. We have some class of functions, and we can homomorphically evaluate this class of functions on vectors of ciphertexts, right? So the only aspect in which a homomorphic encryption scheme differs from a standard CPA secure public key encryption scheme, and the security, as I said earlier, the security notion we're targeting with homomorphic encryption is CPA security, right? We can there is no conflict between having homomorphism and CPA security, whereas when we talk about CCA security, this is a clear conflict, or at least CCA2 security. For CCA1 security, it's still somewhat open whether this notion is achievable with homomorphic encryption, but there is no such conflict when we talk about CCA one and in CPA encryption, right? And the only aspect in which homomorphic encryption differs from non-homomorphic encryption is the existence or presence of such a homomorphic evaluation algorithm, eval, right? And what we're asking for now is just a augmented correctness definition. Security for homomorphic encryption is still the same, CPA security. We just ask for an augmented homomorphic correctness notion, where we say that, well, where we require that give me encryptions C1 to Cn of messages M1 to Mn, and now homomorphically evaluates this such a function f from this class f on the ciphertext C1 to Cn, and then decrypt whatever you get, then decrypt this resulting ciphertext. Then we would like to get the same as f of M1 to Mn. Right? Something that I didn't say last time, but when we talk about homomorphic encryption, we're not asking for the encryption algorithm to be homomorphic, right? When you hear homomorphic encryption, oh, clearly the encryption algorithm is homomorphic. That's not what we're asking for. We're essentially asking for the decryption algorithm to be homomorphic, right? Because what are we having here? We can slightly rewrite this. Oh, what's happening? DEC is homomorphic. We have decryption of using the secret key of this eval PKF C1 to Cn. That's the same thing as I wrote up there. Is the same as, now let me rewrite it on the right-hand side. There I'm just writing f of M1 to Mn. That can kind of pathologically rewrite Mi as the decryption of Ci, right? This is the same as DEC SK C1 until DEC SK Cn. Did we call it? Yes, Cn. So in a way, what's happening now, this we have this homomorphic commutation property, right? So if any one of you went to an algebra course, a mathematician or algebraists really love these commuting diagrams. And that's sort of what homomorphisms kind of give you, right? You're having on the one hand side, on the ciphertext level, you're having this one homomorphism, or as or this one function here, which is just our eval using the public key and our function f and some argument. This is something we have here. Down here we have just the function f, right? And now we're introducing these homomorphisms, or as mathematicians like to call it, arrows. This is the function DEC SK. Right? And we always have a homomorphism when these diagrams commute, right? Basically, it doesn't matter which arrows you walk in this graph, the result will be the same. And there's only like two options. You start from this guy up here, you walk here and walk down there. This is the same as first walking down here and then walking down there, right? So really, when we talk about homomorphic encryption in a strict mathematical sense, what is homomorphic here is the decryption algorithm. The decryption algorithm has a homomorphism property, not the encryption algorithm, right? Because clearly, the encryption algorithm isn't even a function. It takes in additional random coins, produces a ciphertext distribution, and well, such functions that take additional randomness, for those, it's even unclear how to define homomorphism, but in a strict mathematical sense, what's really homomorphic here is the decryption algorithm. Any questions? If not, let's continue and go ahead with our instantiation, right? So to construct this, let's say, first non-trivial homomorphic encryption scheme we want to look at, we need a bit more than these groups of prime order we were working with so far. We need groups of composite order, right? And something that we have seen is that if we have a group here of order, let's call it G, any group G of order P times Q, doesn't matter what the group is, right? Any group, we know two things immediately. This thing, well, because this thing here, or via, I mean, Chinese remaindering and whatnot, this group is gonna be isomorphic to a cyclic group GP times a cyclic group GQ, right? And since P and Q are co-prime, we can deduce that GPQ also has to be cyclic. I mean, we could build a cyclic generator for this group. Right, and if it's cyclic, it's in particular abelian. It's a commutative group. So any group of order P times Q has to be both cyclic and abelian. Great. Good. Now since we're good, this was the same. Still that argument here, but now we're interested in hardness assumptions in such groups of composite order, and something I kind of alluded to is that groups of composite order are, I mean, again, we can write them as always as GP times GQ. They're not that different from, let's say, vectors of group elements, right? If we have a group GP and look at the group GP square, two-dimensional vectors of group elements, that's itself, of course, a group. Composite order groups are not that different, right? On the one hand side, we have I mean, if you take GP squared, that's just can be written as GP times GP. That's a definition, right? And on the other hand, we've seen GPQ. This is just GP times GQ. They're very similar. Right. Now, of course, the subgroup structure in these two groups are slightly different, but in the first group, in this GP square, we've already seen a natural decisional assumption, which was just here we're typically making the DDH assumption, right? Oops. No, what's happening? And down here, we're making something that we call subgroup indistinguishability. Now, DDH is an instance of subgroup indistinguishability, but let's briefly look again at the proper definition. So when we're talking about groups of composite order, we cannot fix an infinite family of groups because these groups need to be privately generated, right? Anyone who knows the factorization of n into p and q will be able to break break some natural hardness assumptions in such groups. In particular, we'll be able to break subgroup indistinguishability. Now, we need a group generator. I've introduced this earlier. And now what are we going to do? Subgroup distinguishing problem asks to distinguish the following two distributions. I always give you the group G, a generator G, and the order n of this group. And now on the left-hand side, I'm giving you G to the R. So G generates the entire group of order n, which is P times Q, right? It generates the entire thing, and I'm giving you G to the R. That's an element from the entire group, right? A random element from the entire group. Comparing this to DDH, this was typically what was the right-hand side distribution of DDH, something, a uniformly random vector of G square, right? That's the analog here. And on the other side, I'm giving you G to the R times P. And I said earlier, G to the P generates a proper subgroup. It doesn't generate the entire group. It generates a subgroup of order Q. There's only Q elements in there, right? This is what sort of the natural analog of this one-dimensional subspace in the case of DDH, right? In DDH, we said either uniform from G square or uniform in a random subspace. Well, here we're not having sort of a random subspace. We're having a subgroup of order Q, something uniform in a subgroup of order Q. Good. And yeah, in other words, as I write here, the subgroup distinguishing problem asks whether an element H that I give you generates or is random from the entire group G, or just randomly chosen in the subgroup GQ, right? And well, we call it subgroup indistinguishability problem because we assume and hope that it is hard distinguishing these two distributions. So even in bilinear groups, we don't have, so that there are bilinear groups of composite order n where we believe this problem is hard. Okay, are there any immediate questions concerning this? So in a way, right, subgroup indistinguishability, you should think of it as a natural generalization of DDH, right? Because DDH is at its core a subgroup a very special case of a more general subgroup indistinguishability problem. So here we're having subgroups of different orders. In DDH, there's only two possible orders for subgroups, right? Namely, well, three possible orders. There's order 1, right? Then it's just the subgroup that just consists of the identity element. There's order P, then it's a one-dimensional subspace, and order P squared if it's the entire space. Right, and here there's really just 4 different subgroups: subgroup of order 1, subgroup of order P, subgroup of order subgroup of order 1, that's just the identity element, subgroup of order P, subgroup of order Q, and the entire group which is order PQ. Whereas in the DDH case, right, there's many subgroups of order P. Every single one-dimensional subspace is a subgroup of order P. Good. I think, by the way, I did mention this a while back. So next week I will be on a workshop, and my student Ricardo will take over. Maybe I'm gonna ask him to do some exercises regarding group theory. Maybe just so we're not moving on in the sort of. Someone have a bell with you? Oh, was your phone? Oh, okay. Oh, sorry. Sorry, I didn't want you to smash your phone. Sorry. Oh, it was just like one of these bells when you check in at a hotel and there's no concierge. You ding, 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 ding. Okay. Good. Okay. So now subgroup indistinguishability. That's the takeaway here. Subgroup indistinguishability postulates that these two things here look the same to any efficient observer. Good. Now that we have this and already spent 20 minutes, let's go into the Bonnet-Go-Nissim crypto system. You can see that, Dan Bonnet was really an early adopter of this idea of pairings, and he really pushed this agenda of building advanced crypto with this back then new algebraic structure of pairings. And good. So the BGN crypto system is not what we now call a fully homomorphic crypto system. So fully homomorphic crypto system allows to homomorphically evaluate the class of all functions, right? Or of all efficiently presentable or efficiently computable functions, right? We have to restrict ourselves to efficiently computable functions if you were to allow have homomorphic encryption for functions that cannot even be efficiently evaluated, that sort of causes friction even with the definition of or can cause friction even with the definition of homomorphic encryption. But the BGN crypto system looks at a very down-to-earth class of functions, namely quadratic functions or quadratic polynomials over essentially quadratic functions over z, over the integers, right? Now, of course, as before with the Elgamal crypto system, we will require that the inputs are short, right? We interpret so we think of the encrypted messages as integers, but integers that have sort of a bounded absolute value. The absolute value cannot be arbitrarily large because, well, ciphertexts are not arbitrarily large. But the BGN crypto system gives us homomorphism for quadratic functions, right? If we were to, for a moment, ignore this part here, this quadratic part, we would just have linear functions, right? A function of the form, beta I mi plus gamma, that's a linear function. And that's something that Elgamal gave us already, right? So the thing that's new here, that goes beyond what Elgamal gives us, are these quadratic terms here, right? And at first, it doesn't seem like much, having the ability to evaluate quadratic polynomials instead of just linear polynomials, but this crypto system here led to, well, yet another revolution in crypto, namely one that concerns proof systems, right? In a much earlier lecture, I talked a little bit about something called zero knowledge proof systems or non-interactive zero knowledge proof systems. It's sort of a generic tool to build actively like CCA secure encryption schemes, right? And until the early 2000s, so the BGN crypto system was published in, I think, 2003. Up until then, we had sort of very, let's say, conceptually contrived constructions of zero knowledge proof systems. Well, these conceptually contrived ones are sort of currently, I mean, last year, this year now, seeing a comeback because they allow, I mean, somewhat surprisingly, for constructions of zero knowledge proof systems from assumptions from which previously we didn't believe we could construct a proof system, but that's a sort of a different story. When it sort of comes to efficient proof systems, right? Systems based on bilinear maps, and in particular the BGN crypto system, still are the front runner. All right, good. But on this slide, we're directly looking at this Bonnet-Go-Nissim crypto system. So what are we going to do? So first, we run a group generator. So here, somewhat sloppily, I didn't give it 1 to the lambda as an input, but the keygen first generates a bilinear group of composite order, right? Let's keep that in mind. Bilinear group of composite order. Next, we choose an element T from Zn uniformly at random. Recall that the group generator, well, the group generator N, we think of the order, the composite order N of such a group as public. So we choose a T of Cn uniformly at random and set H, which will be our public key, so to speak, as G to the T times P. So here, as we said earlier, when we raise something to the P, then this element is immediately in the subgroup of order Q. Right? Raising something to the P, then you're immediately restricted to the subgroup of order Q. And since we raise it with also with a random T, this H is just a random element in the subgroup of order Q. Good. And now, essentially, together with a description of this group, my H is the public key. And the secret key, which we will need to decrypt, is just Q. Okay, so how do we encrypt? Well, encryption is again surprisingly simple. Given the description of this group, this element H and a message M, we just choose a uniformly random R from Zn, and recall once more that since N is public, we can do that efficiently. And just output our ciphertext C as G to the M times H to the R. This is really, again, similar to the El-Gamal crypto system. I don't know why I write it G to the M, H to the R, right? Let's think of it as H to the R times G to the M. I like this, let's say, version a bit more, right? If we compare this to El-Gamal, right? There we basically have some G to the R, H to the R times G to the M. Right there we have this additional G to the R, but again, that's not surprising because there the subgroup indistinguishability assumption we're working with is over, well, the group G square. We're having vectors of group elements. And here, for this type of composite order group, we're not having vectors of group element. This would be El-Gamal here, right? Compare with El-Gamal. Good. Okay. And yeah, so ciphertexts look even simpler than El-Gamal ciphertexts, right? Just because we're using, let's say, a group with a little bit more structure. Okay, and that's encryption. And what does decryption do? So we said the secret key just consists of Q, and to decrypt our message M prime, we just compute a discrete, let's not make that so thick. We compute C to the Q, right? And I recall that I said earlier, when we raise something to the P, we end up in the subgroup of order Q. When we raise something with Q, we end up in the subgroup of order P. So we compute C to the Q, and then we compute the discrete logarithm of this C to the Q with respect to G to the Q. Right? Well, a discrete logarithm, that shouldn't be efficient, right? But that's why I said the message, for decryption to be efficient, the message M should be small, right? And if M is small, or we can compute this efficiently by brute force, meaning we just enumerate all small exponents, let's call them mi, and compute G to the Q to the mi, and check if we get the C to the Q, right? So we can, if the message M is small, we can efficiently compute this discrete logarithm by brute force, just by enumerating all possible messages. But now we're finally getting to the interesting part, and see. So the algorithm I just described is something I called DEC1, right? That's a decryption algorithm which takes ciphertexts that have not been homomorphically evaluated. So a feature of this encryption scheme is that ciphertexts have two qualities. I mean, we can put DEC1 and DEC2 into one and the same algorithm, which just looks if a ciphertext we want to decrypt is a pre-homomorphic ciphertext, so a ciphertext which has not been homomorphically evaluated, or a post-homomorphic ciphertext which came out of homomorphic evaluation, right? And we could, let's say, augment ciphertexts with a flag that says this is a post-homomorphic ciphertext or a pre-homomorphic ciphertext. This is equivalent to me just giving you two decryption algorithms, right? It's easier to write like this than to have a decryption algorithm which makes distinguishes two cases. All right. Good, but the interesting part here is homomorphic evaluation, right? Let's say we're being given ciphertext C1 to Cn, and then, as before, these factors alpha ij, right? These coefficients of the quadratic monomials, the beta I, the coefficients of the linear monomials, and gamma, the constant term, and we do the natural thing, right? So to compute the constant term, we just pair G with itself. We compute EGG to the gamma. To compute the linear term, we first pair the G's with the Ci, and then raise it to the beta I, and multiply that all up. And to compute, again, the magic or the interesting thing happens now here in the quadratic term. We just pair up the Ci's with the Cj's and raise it to the alpha ij, right? So again, here we just think of the pairing to allow us to perform a multiplication of ciphertexts. This is exactly what's happening here. And yeah, that's sort of really the natural thing one would expect here. And deck 2 is also simple. Now here, since the ciphertext now lives in the target group, right? Deck 1 takes ciphertexts that live in the source group and decrypts them. Deck 2 takes ciphertexts that live in the target group, and the generator of the target group is this EGG. And to go into the subgroup of order P, we just raise it to the Q. All right, that's the entire scheme. Are there questions at this point? Yes, good question, finally.
I'm wondering about the log. Is it, you said just brute force it, and then if the m is small, we can just brute force it, and would that be efficient?
Let's see. Good question. Let's see. Let me add. So how was that again? Add page. The new page will be bigger than the rest. Yeah, I don't care.
What if the m is large?
Well, what if m is large? Okay, let's.
Is that two different questions?
No, let's first focus on this question. What happens if m is large? Anyone? Yes?
We cannot compute the log.
Exactly. But why is that not a problem? Well, the correct algorithm, so to speak, right, only gives you a guarantee, a correctness guarantee for if a small m has been encrypted, right? So if you know that every honest user just encrypts small m's, then everything is fine. If there's some jerk who encrypts a large value, well, that will result in a decryption error, right? But we're only looking at semi-honest security here, right? We're not looking at the setting where we have some punks running around trying to spread chaos and disorder. That would be the setting of malicious security, right? Here in the world of semi-honest security, you trust that all users who participate in the system act honestly. They don't try to explode your runtime. Now that's an optimistic scenario, right? Often not good enough for the real world. However, if you want to achieve a strong security notion, right, the first thing with additional functionality, the first thing you should try to get sorted out is getting a scheme with strong functionality, satisfying weak but meaningful security notion, which is CPA security. Right? Often for real world uses, CPA security is not enough. However, it's an incredibly useful intermediate notion to build stronger cryptographic schemes on top. Right? If you want to target a stronger notion, first build a scheme that satisfies the weaker notion, and then try to go from there. Right? So before we want to target a maximalist security goal, let's first look at a moderate but meaningful security notion. Good. That was the second question. The first question was, why should this even be possible? But is it a short question, or should we first do the how to compute D-logs?
I have another short question also about this, but if you want to answer.
So how do we compute D-logs, right? Let's make a very simple setting. Let's say we know that m is either 0, 1, or 2, right? For good measure. It could be just 0 or 1, but let's make it 0, 1, or 2. To show it doesn't just work for m equals 0 or 1, right? And now my ciphertext, let's see what, let's look at deck 1, right? Deck 2 works the same way, but my ciphertext is something like h to the r times g to the m. Okay, now I'm already going a bit into the correctness proof here, right? What happens if I take this ciphertext here, C, and compute C to the Q, right? That's what decryption does, is it computes C to the Q. Well, this is nothing but H to the Q to the R times G to the Q to the M. I've basically flipped the order of exponentiations, but that's fine, right? We've all learned that in high school math, that this is possible. Okay, but recall that we said that H is something of the form G to the T times P, right? This is now G, whoops, oh, not Q. G to the T times P times Q to the R times, again, G to the Q to the M. And G to the T times P times Q, what's that? P times Q is N. What happens if we raise a group element to the group order?
Group identity.
Exactly. This is 1 equals 1. That's a very simple consequence of Lagrange theorem, right? I think I said that numerous times, but now C to the Q is just G to the Q to the M, right? And again, I said earlier, here we're just looking at the semi-honest setting. We assume the encryptor was honest. So M is either 0 or 1 or 2, right? So this is now either G to the Q to the 0, which is 1, or G to the Q to the 1, which is GQ, or, well, GQ square, which is G to the 2Q. Okay, and that's just 3 possibilities. I can test all these 3 possibilities by given, 1, right? I can test if something is 1. I'm being given GQ. I can G to the Q. I can compute that, right? Q is the secret key. So I said we're computing D logs with respect to G to the Q, and so testing if it's G to the Q is also easy, and well, GQ square you can also easily compute. So you really just have to do 3 tests in this case. And as long as this domain from which n could possibly come is just polynomially large, this is efficient, right? We can just enumerate all possibilities for M and test every single one of them. So, yes.
Not to nitpick, but I might be very confused. Is that or equal sign?
Or this is sorry, here this shouldn't be thank you. No. Or we have these 3 possibilities, right? Good to nitpick. I do this quite frequently. But okay, I think that resolves this question. Please, what was your question?
It's about deck 1 and deck 2.
Yes.
But if you could maybe reiterate again about what the difference between them is, because I see the deck 2 associated with the identity of the bilinear map.
Mm-hmm.
I didn't really understand what the idea is behind.
Look, I think I don't know why use deck 1, deck 2 here. You could do everything with deck 2, right? If you get let's say a ciphertext of quality 1, a ciphertext in the source group, you could just pair it up with G and then run DEC2. Would give you the same thing, right? So, yeah, I don't know. I don't know why I back then when I wrote this made this decision, but again, just tells you to be. I mean that nothing is carved in stone, right? Yeah, an alternative way of doing DEC1 would just be to take your ciphertext and pair it up with G, right? Then the same thing that happens here, right? You take a cipher in the homomorphic evaluation, you take these CIs and pair them up with G. But okay, so this here was in essence already the correctness, the not yet homomorphic correctness, right? We realize that basically C to the Q is again this H to the Q to the R times G to the Q to the M, which this is 1, is just G to the Q to the M. And now the D log, let's put it underneath, the D log with base G to the Q of this will give us M. Okay, that was the correctness, and yeah, this D log, as I said earlier, this D log to the base G to the Q is efficient as long as we can efficiently brute force M, all possibilities for M. But let's so good. Wow, why did I go for 3 slides here? Let's look at homomorphic correctness. The more interesting right? Let's first look at a homomorphically, this I think we can close, a homomorphically computed ciphertext. Let's say C1 is H to the R1, G to the M1, and Cn is H to the Rn times G to the Mn. Right, and now let's compute a homomorphic ciphertext. Let's call it C star, which is now the product I comma j. I think we're going just over ij, yes, over ci e ci cj to the alpha ij times product. Here we go over all I. E g comma ci to the alpha I times e g g to the gamma. Right? Now let's write out this ciphertext into 2 components. I mean, obviously the message will reside with respect to this generator EGG, right? So let's write out all of these CIs. Let's do that. Let's do that very slowly, step by step. So CI is just H to the Ri times G to the Mi, comma. Here the Cj is H to the Rj times G to the Mj to the alpha ij. Right? Then we still have the linear part, which is Eg comma H to the Ri times G to the MI times alpha I and E G comma G to the gamma. Okay, now let's use the bilinearity of our pairing, right? You know what? Instead of going, I think we can sort of take a shortcut because decryption takes such a homomorphically evaluated ciphertext and raises it to the power. Let's just leave that here. Come on, it's my battery. No. There it goes. Good. Let's look at C star raised to the power Q, right? So what happens now if we take the right-hand side and raise it to the power of Q? Let me think if this is a good idea. Actually, no. I think doing it step by step will be more insightful than doing than jumping ahead here. Good. Let's do this step by step. Then and let's now separate, so to speak, the the mixed terms, right? When we're expanding the pairing, when we use bilinearity, we will have sort of terms in which we have H and H and G and H, and G comma G, and the messages, they only reside in the EGG parts. And now let's separate the EGG parts from the mixed terms, the gross terms in which ages appear, right? Let's do this. So if we take this, this is just every single one of those is just E of H to the Ri, comma H to the Rj to the alpha ij times E of H to the Ri, comma G to the Mj to the alpha ij times, I'm writing it underneath to have some more space, E of G to the Mi, comma H to the Rj, all right, to the alpha ij. This is one part, right, times now the part I'm interested for correctness is E of G to the Mi, comma G to the Mj to the alpha ij. And for good measure, let's give this term here a name, and let's call it. Could I call it H? Oh, I already have T's. What could I use? Let's call it capital Aij. Okay. This thing will now be capital Aij, and here we can do something similar, but much easier. This thing here, if we multiply that out, that's just Eg comma H to the Rj. Sorry, Ri. Ri times E of G comma G to the M I to the alpha I to the alpha I. Okay, and well, these things, let's just call them for good measure B. Oh, too close. Oh my God. BI. Okay, so we get that. Let's hope he doesn't try to save my eyes again very soon. What we get is that C star is product I comma J Aij, right? Times product I comma J. Now let's look at this part here and rewrite that as E comma G to the alpha ij mi mj. Okay, this is again just bilinearity. So here we have E G to the alpha ij mi mj, and we do the same thing here, times product over all I bi. Let's put a few more parentheses here. Bi times product over all I E G to the beta I mi. And the last but not least, we have this EGG to the gamma term. Okay, I somehow have to switch this off. But so far, we all agree. And now let's simplify it a tiny bit more, or rearrange it a tiny bit more. So we have here the product I comma J Aij, product I bi, and now we have EGG to the sum. Right now all these terms here have bases EGG. So instead of taking a product over group elements, we can just take the generator and raise it to the sum of the corresponding exponents, right? So this is the same as EGG to the sum I comma J alpha ij mi mj plus sum I beta I mi plus gamma. Okay, we've really so far just rewritten this the expression for this ciphertext C, for this homomorphically evaluated ciphertext C star. We haven't changed anything about it. And now let's take C star to the Q, right? What is this? Well, this is this product I comma J Aij to the Q times, well, product Bi to the Q. And the third part here, I'm just going to write it as EGG to the Q to the sum Ij alpha ij mi mj plus sum beta I mi plus gamma. Good. So what do you have to show now in order to establish homomorphic correctness of this scheme? What would we like this expression C star to the Q to be? Recall that after we compute this C to the Q here, we take a D log with respect to EGG to the Q, right? already written this part here as EGG to the Q, right? So if this C to the Q was just the stuff that's in the red box now, then our scheme is correct. What does that mean for the other stuff? What do we have to show for that? Yes? Exactly. This stuff should all be one, or the identity. And how can we do that? Let's first look at the well, this is, of course, instead of raising to the Q out here, we can raise to the Q in here, right? It's the same thing. So what is Aij to the Q, right? Our Aij, well, is this expression up here. It's E of H to the Ri, comma H to the Rj, Rj to the alpha Ij, and now times Q, right? Already using pulling in the Q here, times E of H to the Ri, G to the Mj to the alpha Ij times Q, comma, E of the G to the Mi, comma, H to the Rj, alpha Ij times Q. That's it. And now I'm just pulling in the Q. I'm using bilinearity again. And this is the same as E of H to the, let me write it directly like this, H to the Q to the Ri, comma, H to the Rj, alpha Ij, times E of H to the Q to the Ri, comma, G to the Mj to the alpha Ij, times E of G to the Mi, comma, H to the Q to the Rj, I said, Rj to the alpha Ij. So these guys, what do we know about them? H to the Q. We said H is G to the P times whatever something. What do we know about? So H sits in the subgroup of order Q. I don't know that you know it, but anyone else in the audience? Yes?
They are all one.
They are all one, exactly. So this guy is one, this guy is one, and this guy is one. And what happens if we pair something up with one? What happens then? Recall that one is G to the 0. Right? I mean, we already had that in the definition of bilinear maps, but if you pair something up with one, the resulting thing is one in the target group, right? Because again, you can always write one is G to the 0, and if you now E of one and let's say something F whatever, this is E of G to the 0, comma F, but now you can pull out the 0 and have this, this is E to the G, comma F to the 0, and raising something to the 0 is always 1, right? That's a simple way to remember this. It's maybe not the mathiest way to derive this, but there's other ways of doing this. If you pair something up with 1, right, multiplicatively 1 is the neutral or the identity element, and if you pair up something with 1, the only consistent way to define the output is this to be also the identity element, right? Good. So we have Aij to the Q is 1. So this is 1, and likewise B BI to the Q is also 1, right? Because there we also the BI to the Q, you have E, G, comma, H, exponentiate this with Q, and you have a pairing of G and H to the Q to the Ri, and the right hand side will be 1. Okay, so you know what? Let's add an extra slide here. I don't want to rush this add page. So likewise, BI to the Q is E of G comma H to the R H to the Q to the Ri to the beta I. Right? Did we have the beta I here? Oh no, why did I call it alpha I? It should be beta I. Beta I, beta I, beta I. Let's hope I called it. No, I also called it alpha I up here. It should be beta I. I think now we're good. To the beta I, but this guy here is just 1, right? And now again, we're pairing up G with 1. This is just 1. So we do have C star to the Q is just E, G, G to the sum ij alpha ij mi mj plus sum I beta I mi plus gamma, right? And now if we take to the Q, of course, this is E G G to the Q to the this. If we now take the D log with respect to E G G to the Q of this, we will get sum ij alpha ij mi mj plus sum I beta I mi plus gamma. And therefore, scheme is correct, or we get homomorphic correctness. All right. And of course, again, we can only efficiently compute this discrete logarithm if we know a priori that this exponent here, this sum ij, alpha ij, mi, mj plus sum I, beta I, mi plus gamma is small, right? So we don't just require that the mi and mj are small, but also that these coefficients, alpha ij, beta I, and gamma are small, right? So if you know ahead of time that the alpha ij are small, that the beta, yes?
Can you give some bounds on small? Like how small are we talking?
Polynomially large. I mean, as soon as you can efficiently enumerate all the resulting values, right? And now, of course, polynomial is an asymptotic notion, right? You might, in practice, you can just bound the size of the exponents if you have a bound on the if you have a bound on the size of the alpha ij, on the beta I, and on the mi and mj, then you can compute a simple bound on these. For instance, let's do this. Let's do this for concreteness. Let's say all the absolute value of the mi is smaller or equal than what let's call it delta, then some parameter delta, right? Let's further assume that all the alpha, all the alpha ij and the beta I and the absolute value of gamma is also smaller than delta, right? And delta, this is some polynomial, then well, let's compute the absolute value of some ij, alpha ij, mi, mj plus some I beta I mi plus gamma, right? First thing we can throw at this is the triangle inequality, right? The absolute value satisfies the triangle inequality, so this is smaller than sum I. I'm going to do that with all sums in one go. Alpha I j, but now products, the absolute value of a product of any number of values is just a product of absolute values, right? mi, mj plus some, now over I, we have beta, I'm going to make a new page, beta I mi plus gamma, that's, and good. These guys here, right, each of them is smaller than delta. So this is smaller than delta to the 3. This is smaller than delta squared because beta, the absolute value of beta I is smaller delta, of mi smaller delta, and this is also smaller equal delta, right? So and this first sum goes over n squared terms. So the overall thing is smaller than n squared delta to the 3 plus n times delta square plus delta, right? And let's be just very asymptotic. This is O of n squared delta to the 3. And n has to be a polynomial. We said delta is a polynomial. So this is poly lambda, okay? So if all parameters here are in some sense delta bounded, then the output value of our function is n squared delta to the 3 bounded. And if delta was a polynomial, this is still a polynomial, and we can efficiently brute force over the set of all potential output values, right? And therefore, decryption is efficient. So how much time do we have left? 15 minutes. Good. Let's go to CPA security, right? For CPA security, I'm not gonna do the reduction in all its glory. Let's do that sort of efficiently, time efficiently, how most people do these security proofs in their work, right? We've seen the entire machinery of doing explicit reduction at work, but now let's take our, let's say, a challenge ciphertext, let's say a public key, right, which was consisting of G, generator, and N, as well as this group element H, and recall that H was something like G to the T times P. That's our public key, right? In CPA security, the adversary gets the public key, chooses two messages, and then gets a challenge ciphertext C star, which is H to the R times G to the MB. Okay, right? And the adversary's goal is to guess MB. So let's call this is our hybrid 0, the real experiment. Right? What's the hardness assumption we want to use to prove security of this scheme? What's the hardness assumption I talked about earlier? Who paid attention an hour ago? Yes. Subgroup indistinguishability. So recall subgroup indistinguishability. We said that G, comma G, and the order n given G to the T times P is indistinguishable, or let's write it underneath, indistinguishable computationally from, again, the group representation remains the same, but now we just drop this P and just write G to the T, uniform element from the whole group. And well, where someone now tell me, where can we use this this assumption? What component of this scheme are we gonna modify in CPA experiments? Are we gonna modify the ciphertext? Who's in favor of modifying the ciphertext, the challenge ciphertext? No one. Who's in favor of modifying the public key? 1, 2, 3, 4, 5. Okay, yes. So look at this value here. This H, which is G to the P. So clearly in hybrid 1, we just set our public key to be G, comma G, N, and now our age is G to the T. And C star is still the same thing. H to the R times G to the MB. Okay, so what would happen if we had an adversary who can tell these two hybrids apart? Well, we could directly use him, of course, right? But I'm not going to do that now in all its glory, to break the subgroup indistinguishability assumption. Because what are we going to do? Well, a standard reduction. The reduction gets an instance of the subgroup indistinguishability assumption and just uses this group, this generator G and H, together with H as a public key, and does everything else as the InCPA experiment would do. If our H is of the form G to the G to the T times P, then we simulate H0 faithfully. Whereas if it's of the form G to the T, we simulate H1 faithfully. Means an adversary who distinguishes H0 and H1 could immediately tell these or distinguish the subgroup indistinguishability assumption. Okay, and hence we have H0 is computationally indistinguishable, meaning the advantage of an InCPA adversary in H0 cannot be negligibly cannot be further than negligibly close to that of the same adversary in H1. Good. By subgroup indistinguishability. distinguishability. So now the interesting thing happens in H2. There's not going to be an H3. In H2, the public key is still going to be G, GN, H, which is G to the T. But now my C star is just, let's say, uniformly random in G, i.e. Something like C star is G to the Z. And that's obviously independent of the bit B, right? If I choose my ciphertext uniformly random, then the advantage of our adversary in H2 is 0, right? So first observe the advantage of adversary. I didn't call it A, of adversary in H2 is 0. C star is independent of the bit B. Whoops. So all that we have to show is that H1 and H2 are indistinguishable. We're going to show something even stronger. They are identically distributed, right? Even if you have infinite computational power and you have infinite luck, you wouldn't be able to tell H1 and H2 apart. How can we do this? Well, let's just go ahead and write out our well, there's not a lot to do here. Write out our C star, right? In H1, C star is H to the R times G to the MB. But we said that H is just G to the T. This is G to the T times R plus MB. Good. Actually, what I just said is not correct. They are just they're not identically distributed. They're just statistically close. So we know that R is uniform. Uniform. If R is chosen uniformly random, what do we know about T times R plus MB? Well, ideally, we would like to say this is also distributed uniformly random, and this is almost true, right? What do we need to establish that this is under what constraint is this uniformly random? So clearly, if T is 0, then this is not uniformly random. Then we have 0 times R plus MB, not good, right? But we also know that T is uniformly random. But information theoretically, the adversary knows what T is because it's given by the public key. You could just recall that we want statistical security now. The adversary could just compute T by computing the D log of H with respect to G. That's exactly T. So what's the we're in the group G, what's the order of the group, capital G? What is, yes? N. It's lowercase n, exactly. So basically, we want to look at T times R plus MB modulo n. Right? This is the order of the group is the order of the group is n. So, oh, now I've talked so much. There's only 4 minutes left, but we're gonna finish this. So, clearly, if T element, I'm gonna speed it up. If T is a unit modulo n, right? If T has a multiplicative inverse, right? Then I claim then T times R plus MB is uniform, right? And seeing this is easy, right? Why is this uniform? What's the probability that T times R plus MB is some value X? Well, let's solve it for R. This is the same as probability T times R equals X minus MB, right? But now I said that T has a multiplicative inverse because it's in the unit group. This is the same as probability R equals X minus MB. Let's write it times T inverse. But R is chosen uniformly random, right? So this is just 1 over n. Good. So if the probability that T times R plus MB is X is 1 over n, irrespective of X, then we have T times R plus MB equals is uniform. Is uniform. And there's just one last thing. I have 2 minutes left. For this to hold, we need that T is in Zn star. What's the probability that, not you, Jesko, that a uniform T is in the unit group? What's the size of the unit group? What is our probability T element Zn star? This is obviously, right? A T is chosen uniformly at random. Size of Zn star divided by, well, size of Zn, but this is just, this lower thing is just n, right? So we divide by n. So what's that? What's the size of Zn star? Yes? It's phi of n. This is phi of n divided by n. So phi of n divided by n, is that something, what's that value, right? I mean, we just heard this is p minus 1 times q minus 1 divided by p times q, right? And oh, well, this is just 1 minus or 1 over p times 1 minus 1 over q, right? Which is 1 minus 1 over p minus 1 over q plus 1 over pq. Well, and p and q are both large primes, right? Therefore, this is 1 minus negligible. and we're good, right? So except with probability, except with negligible probability, T is a unit, and if T is a unit, then T times R plus MB is distributed uniformly, and therefore, in this case, hybrid 2 and hybrid 1 are identically distributed. Therefore, hybrid 1 and hybrid 2 are statistically close, right? So unless T is not a unit, they're identically distributed, and therefore they are statistically close. Good, and that concludes this lecture. I'm just 1 minute over. Are there still any questions about this? If not, then thanks everyone. And as I said, next week we will have Ricardo with an exercise session. All right. Thank you so much.